So in this video, I want to talk about section 11.7. I'm not going to tell you anything new. There's no new tests, but just like when we did integration, there was a section specifically dedicated to just throwing, in that case, it was throwing integrals at you, and then you had to figure out what methods are we doing: substitution, integration by parts, trig substitution, partial fraction decomposition, and you didn't have any idea what the integral was ahead of time. In this section, it's the same. It's just series. So we're going to give you a series. And what we want to do is we want to decide, are we going to use the test for divergence? Are we going to use the comparison test, the alternating series test, the integral test, the ratio of the root test? And so what I want to do in this video is in class together, we'll talk about lots of examples where I just give you lots of series, and then we have to decide, did they converge, do they diverge? And that'll be the story. That's what we're going to decide. And so in this video, what I wanted to do is just to kind of look back at all the tests that we have so far, think about what are the hypotheses for the tests and when do they apply, and then what are some examples where they're useful. And so that's what I want to do. And so in 11.7, this is strategy for series. And we know the following tests. So in 11.2, we know, I guess this isn't really a test. So the first one I'm going to write down is actually less of a test, but we know that x to the n from 0 to infinity converges to 1 over 1 minus x if and only if the absolute value of x is less than 1. The book words this a little bit differently. It turns out that when you have the sum of x to the n as n goes from 1 to infinity, this is just the sum from 0 to infinity minus the n equals 0 term, which is 1. X to the 0 is 1. And so this is 1 over 1 minus x, as we know, minus 1. So that's 1 minus the quantity 1 minus x over 1 minus x, and you get x over 1 minus x. And this is the formula that the book gives. They use r's instead of x, and they have a constant in front. So they have a r to the n, and so they have a, and then their x's are r's. That's the formula they give. Everything comes down to knowing this formula, which is valid if the absolute value of x is less than 1. So I think this is an easier way to go for geometric series. But that's everything that you need to know about geometric series. We know when they converge, and we know what they converge to, okay, which is more than we know for most series. So that's geometric series. Other series that we've looked at would include things like the divergence test, or sometimes called the test for divergence. And here, what we're doing just in general, I'm going to look at the series a sub n as n goes from 1 to infinity or 0 to infinity or whatever. Okay, that's really the kind of base series that we're looking at. And the divergence test says that this series diverges if the sequence a sub n does not converge to 0. So if the sequence diverges, like if it's -1 to the n, or if it converges to some number other than 0, then the series diverges. Okay, so that's the divergence test. So the series diverges if the sequence does not converge to 0. We also learned the integral test. So the integral test says that if you have a function f of x where f of n, so when you plug in integers, you get the sequence a sub n. And if f is positive, so greater than or equal to 0, decreasing, and continuous, you need continuity so that the integral is well defined. I mean, continuity is only there to ensure that there's the integral you can evaluate. But as long as the function's positive, decreasing, and continuous, and actually I should mention, we're kind of getting into the weeds here, but decreasing to 0, because if it's decreasing but it asymptotes at 2, then you know that if you have a sequence, then the divergence test applies and the series diverges anyway. So that actually doesn't help us. So the integral test, it's really useful only when you have a function that's non-negative, so it's greater than or equal to 0. It's decreasing to 0 and is continuous. Then if it meets all these criteria, then the sum converges if and only if the series converges. So if and only if the series, the integral converges. So the series converges if and only if the integral converges. And almost definitely they will converge to different values. But what we know is that if one is finite, so is the other. And if one's infinite, so is the other. So that's the integral test. Okay. After that, we talked about the alternating series test. So I went slightly out of order here. This is actually, so the divergence test was 11.2. The integral test was 11.3. Alternating series were actually 11.5. So the alternating series test says that if you look at the sum from, so -1 to the n, b sub n, where b sub n is positive and decreasing to 0. So if b sub n is positive and b sub n decreases to 0. When I say decreases to 0, by the way, and I've said that, I said that above, just what I mean is that the sequence is decreasing and its limit is 0. So just to be concise about what I mean there. So if b sub n is greater than or equal to 0 and decreasing to 0, then the series converges. Okay, so then the series converges. That's the alternating series test. The comparison tests were what we talked about next, even though that was section 11.4. So the comparison tests. And there were two of those. There was the just kind of the standard comparison test. Okay. And the comparison test said that if a sub n is less than or equal to b sub n, here we're assuming a sub n is less than or equal to b sub n for all n. I'm going to write it up there. Then this is organized terribly. Let me fix that. So assume a sub n is less than or equal to b sub n for all n. Then if the sum of the terms b sub n converges, and again, my inner mathematician is annoyed at the wording, but if the series b sub n converges, then the sum of a sub n converges too. Okay, and so just intuitively, this says that if the values in the sequence a sub n are smaller than b sub n, and if the sum of all the values of b sub n converges, then the sum of the smaller values converges too. Hopefully that's reasonably intuitive. Also, there's a second part to this first comparison theorem. Also, if the sum of the smaller terms diverge, then the sum of the larger terms diverge. Okay, so that's the comparison test. And then there was the limit comparison test. And the limit comparison test says if the limit of a sub n over b sub n is some positive and finite number, so if the limit is 1 or 5 or something, then the sum of a sub n, sorry for my dog in the background, but the sum of a sub n converges if and only if the sum of b sub n converges. Okay, so that's the limit comparison test. And then finally, the ratio and the root tests. So the ratio and the root test say, look at the limit L, which is the ratio of consecutive terms, a sub n plus 1 over a sub n, or L is the limit as n goes to infinity of the nth root of the absolute value of a sub n. If L is less than 1, then the series converges absolutely. If L is bigger than 1, then the series diverges. And if L is equal to 1, then the test doesn't tell us anything. Okay, so that's the ratio and the root tests. So we'll do lots of examples in class looking at different series, figuring out what are the right tests. What are the, do we use the comparison test, the limit comparison test, the ratio, the root test? Maybe lots of them apply. And I kind of want to look at series and figure out, are there multiple tests that apply? Maybe, maybe not. So we'll do lots of examples in class, as I said, but this is a brief overview of all the series convergence and divergence tests that we know.